Hello everybody, this is the second video associated with chapter 4, chapter 7 of the reinforcement learning course. So this chapter is about the n-step temporal difference methods which generalize the one-step methods seen in chapter 6 and also the Monte Carlo methods seen in chapter 5. So in the first part of the chapter, we introduced the n-step algorithms for the prediction problem, where a policy was fixed, and then we tried to predict the value function associated with the problem and the policy. And after that, we introduced the n-step version of on-policy learning methods. So for the remainder of this chapter, we will discuss off policy n-step temporal difference methods. Okay, so what's off policy again? It's when you have two different policies. One policy called a behavior policy is used to generate the episodes, and we denote this policy by B, whereas the other policy, known as the target policy, is the one that is currently being refined and which shall attempt to converge to the optimal policy. Okay, so typically, as we discussed before, pi here, which is our target policy, will be a greedy policy with respect to the current action value function estimate. So pi is as close as possible to the optimal policy, whereas B typically tends to explore more, so to try the various state action pairs and to have a faster refinement of the estimates of the various state action pairs. So B typically explores more, whereas pi is more greedy and tends to lay all its eggs in the same basket, which is the greedy action in all states. Okay, so for the n-step method, once again, as for Monte Carlo methods, we're going to use importance sampling. Okay, so as we said, we have two different policies. We generate episodes with the behavior policy B, but we want to estimate the value function under another policy, which is the policy pi. So to reflect the fact that the probability of encountering an episode, a given episode, under respectively the behavior policy B or the target policy pi, they differ. We're going to multiply the various returns by some correcting factor, which is called the importance sampling ratio. And this importance sampling ratio, as we said, reflects the fact that the probability of facing two different or of facing a given episode under the two different policies is different. Okay, so for example, if a path or an episode is twice as more likely under the target policy than under the behavior policy, when we face some reward or return under the behavior policy, we might multiply it by a factor of 2 to reflect that this episode is in fact twice as more likely in practice if we use the target policy. Okay, so the difference here is that the importance sampling ratio definition will be slightly different in the context of n-step methods. So for Monte Carlo methods, if you recall, the importance sampling ratio was the relative probability of each action in the episode under pi divided by their respective probabilities under the behavior policy B. But this was until the end of the episode, whereas here for the n-step method, the importance sampling ratio will stop after n-step. So you don't need to go until the end of the episode because the target policy do not consider actions beyond the next n-step because instead of considering subsequent actions, the target uses bootstrapping and does not rely on actions beyond the next n steps. Okay, So first, we will discuss the prediction problem in an off policy setting. So again, what's the prediction problem? It's when we have a fixed policy pi and we want to estimate its value function. Okay, so we can use off policy learning for that. So what we would do in that case, we would generate episodes under policy behavior policy B, and then we would use the following update rule to refine our estimate of the state value function. Okay, so at time t plus n, we're going to use the following update rule. So for all states S, which are in the time t state, no update is made. But for the state visited at time t plus n, we're going to update its value through the following rule. So the next estimate is again the previous estimate plus the learning rate times the following importance sampling ratio times the target minus the current estimate. Okay. So first, let's look at the importance sampling ratio. This is rho t until t plus n minus 1. So if we look at the definition of this guy here, rho tau h, it's the product for k goes from time t to here, minimum between h and this guy. What's this guy again? This guy is the time at which the episode ends minus 1. The current episode ends minus 1. Okay, so basically this says that this product contains these terms for all time steps until one step prior to the end of the episode, if the episode finishes before the first 8 steps, or if the episode doesn't finish before the next 8 step, then this product contains exactly terms for t plus 1, t plus 2 until time h. Okay, so here what we see is we have rho t plus n minus 1. Why do we stop at t plus n minus 1? Is because we're going to see the last action that is involved in the calculation of the target here is the action at time t plus n minus 1. Okay, so because we're weighting relatively the probability of the various actions under the target policy and the behavior policy, we must consider all actions within the target for such purposes, and we're going to see that the target considers actions from time t to time t plus n minus 1. So this is why we have this important sampling ratio, which ends at t plus n minus 1. Okay, and furthermore, the target gt t plus n, it's defined exactly as what we did for the n-step TD method discussed earlier in the chapter. Okay, so now the other question is this importance sampling ratio. Why doesn't it multiply only g, but why does it also multiply the previous estimate v? Okay, so this is a very good question. We're going to answer that shortly. Well, in fact, we're going to answer it now. So, first, we show here that, let's go back one slide, multiplying the current estimate by rho instead of only this guy, we're going to see we're not introducing bias in our algorithm. So why is that the case? So here, when we weight the current estimate by the importance sampling ratio, we have the following. So the expected value under the behavior policy B, which is the policy under which we've simulated our episodes, of the importance sampling ratio times the current estimate of the state of the value of the state st, given st, is, so here, equal to this. Now, because this guy, it's a function of st, it can be treated as a constant when we condition on st, and we can take this guy out of the conditional expectation. Now there's a quick footnote here which explains why this is not entirely correct, but we'll go back to this later on. Okay, but for now, let's say you can do that. So this becomes the expected value of the importance ratio itself. And here we saw earlier that the expected value of the importance sampling ratio is always equal to 1. So this is indeed the current estimate of the state. Okay, so in expectation, multiplying the importance sampling ratio by the current estimate still is the current estimate, so we're not introducing bias in our algorithm when we do that. Okay, so one quick note, if you want to remember why the expected value of the importance sampling ratio is always equal to 1, please go back to chapter 5 where this question was discussed. Now, a quick note here, if we look at the footnote 3, what we said earlier is that, okay, capital ST, once we condition on ST, this is something that is known, so this term can be treated as a constant and taken out in front of the conditional expectation. Well, this is not entirely true in practice because although ST is known, if you condition on ST, this function, which estimates the value of state ST, this one changes through time. Okay, so this function is not yet known by time t, it's only known by time t plus n minus 1. Okay, so although st is constant at time, can be treated as a constant if we condition on st, the function v cannot. However, in practice, because updates on the value function are very small, this guy will approximately be equal to vt. Okay, and in this case, we could take out this term in the conditional expectation because vt is a quantity known by time t. Okay, so this is not entirely true, but it's a very, very good approximation of the reality. Okay. Now, so we said by multiplying the current estimate by the importance sampling ratio, we don't introduce bias, but why do we do that? Okay, it doesn't give us a valid reason of why we want to do that. It's because remember, the importance sampling ratio, it can be very volatile in practice. Okay, so let's go back 2 slides. So for example, this is a ratio. So if b is very small for some actions, then this ratio can either explode, become extremely large, or if pi is very small for some actions, then this ratio can become very small. So the importance sampling ratio, it can be very volatile with an extreme variance. So what would happen here is that if we only weighted the return by the importance sampling ratio, then we would have this times the importance sampling ratio being very volatile, and this guy, if it wasn't multiplied by the importance sampling ratio, it would be very stable. So the difference of something very volatile and something very stable will have a very high overall variance, and thus the update rule here would lead to very volatile estimates for the value function. So by multiplying both the return and the current estimate by the importance sampling ratio, well, if this guy fluctuates a lot, at least you won't have a very large term minus a normal term. You'll have either two very large terms in average or two very low terms in average. So this stabilizes the algorithm. So we showed multiplying the current estimate by the importance sampling ratio. 1, it doesn't introduce bias in our algorithm, and 2, it greatly reduces variance, which should improve the estimation of the value function much faster. Okay. So, okay. As for Monte Carlo methods, we have to recall the fact which justifies the previous algorithm that the expected value when simulating an episode under policy B of the importance sampling ratio times the return is approximately equal to the expected return, which we would like to calculate under the target policy pi, which is the policy for which we're interested in determining the value function. Now for Monte Carlo, this was exact. It wasn't approximate, it was exactly equal. Now, why do we have this approximation? It's because in the target, recall that the last term here is the bootstrapping term, which estimates the expected value of all rewards after time t plus n through the current estimate of the value function. Okay, so if our estimate of the value function in n time steps was exactly equal to the true value function, then this equality would be exactly equal because the return would be an unbiased estimate of the value function. But now, because we use this bootstrapping term where we have an approximation, this relationship, it's not exactly true, it's an approximation. Okay, but nevertheless, we hope that this approximation is very good. The larger n is, the less reliance on this bootstrapping term we have because of discounting. So the less bias we would have. And for that reason, this almost equality justifies why the value function estimate should converge to the true value function here as t goes to infinity. Okay, recall once again that if so when we calculate the importance sampling ratio, this guy here, at the numerator we have the pi probability, so probabilities under the the target policy of selecting the various actions A in state K. Okay, so if some actions along the episode are non-greedy with respect to the current estimate of the value function, then these probabilities would become zero because pi is a greedy policy and only assigns positive probabilities. Well, in fact, a probability 1 to the greedy action. So in that case, importance sampling ratios would become zero if some non-greedy actions are selected. And if we go to the update rule here, when this guy is zero, there's no update performed. Okay, so we see that by using this technique, although in theory it's very good, in practice there are multiple instances where there's just no update done because the importance sampling ratio is zero, so this can tremendously slow learning in practice. Okay, so as we said, sometimes whenever a non-greedy action is selected, the algorithm doesn't learn, and so moreover, it's how can I say that? The behavior policy is meant to explore, so it's normal that it's going to often select non-greedy actions. So depending on how much exploration is done by the behavior policy, too much exploration might slow the process because of this feature. So we had the same problem in Monte Carlo in chapter 5, but now the problem is less severe for n-step methods. Why is that the case? For Monte Carlo, you looked at all actions until the end of the episode. So as soon as there's one non-greedy action in an episode and the rest of the entire episode, then the episode importance sampling becomes zero. Whereas for n-step, if you only consider the few, let's say n is equal to 3, you only have to look at the next 3 actions, and if one of the next 3 actions is non-greedy, then you put a zero weight, but there are much less actions to check in the n-step method than in the Monte Carlo method. So it's much less likely that the weight for an episode is set to zero because you have much lesser chance of exploring in that case. Okay, so this was the algorithm for TD, n-step TD for in an off policy setting. Now, instead of considering the prediction problem, we can go to the control problem where instead of having a fixed policy, we have some policy that is refined through time. So again, we can use the same exact strategy defined before. We can use the generalized policy iteration procedure where we have some few policy evaluation steps to refine the estimate of the action value function, and based on this estimate then you can apply policy improvement and improve your policies so as to hope to converge eventually to the optimal one. Okay, so for the n-step method we can once again have an n-step sarsa method, so take the sarsa algorithm and make it n-step, but we can have an off policy version of the algorithm. Okay, so previously in the chapter we've discussed on policy n-step sarsa. Now we can do off policy n-step sarsa where episodes are simulated with a behavior policy, and then we can use these episodes to refine our estimate of another policy, which is the target one. And again, the same thing that changes with respect to the on policy setting is that rewards must and returns must be multiplied by the importance sampling ratio to reflect the disparity of likelihood of the various episodes under the behavior and the target policy. Okay, so if we go to an off policy sarsa algorithm, the algorithm looks like this. So at time t plus n, whenever the n step target is observable, we can refine the estimate of the current state st and current, which was current at time t. So if we're at time t plus n, it's not current anymore. But at time t plus n, we can update the value of state st and action at through again a similar type of formula. Next estimate is the previous estimate plus the learning rate times the importance sampling ratio times target minus the previous estimate. So this is pretty much like the n-step TD method we've just seen, except that instead of having a state value function v, you have an action value function. And we have one slight difference here is that the rho, importance sampling ratio, instead of starting at t, it starts at t plus 1, and instead of finishing at t plus n minus 1, it finishes at t plus n. Okay, so we're gonna go back to this. Why do we have these indices for the n-step version? But first, about the target here, the target is exactly analogous to what we did in the on policy case. So the n-step target for sarsa is the sum of the next n discounted rewards. So we say n, but if the episode finishes before that, then we consider all discounted rewards until the end of the episode. Plus, this is the an indicator which tells you does the episode end before the next n steps. If this isn't the case, then you have this bootstrapping term, which is gamma n, so the discount factor in the n step for n steps, times here qt plus n minus 1 in state st plus n and at plus n. So this attempts quantifying the expected rewards the expected return in n steps when you are in the state st plus n and at plus n. Okay, so just okay. Okay, so that's it. Now we're going to go back to discussing what we said earlier about the importance sampling ratio. Okay, so why do we use rho t plus 1 to t plus n instead of rho t to t plus n minus 1? Okay, so first, why do we start at t plus 1 instead of t? It's because in the TD, we did not prescribe the action at time t. The action at time t was selected based on the policy behavior B. Whereas for the end step sarsa, sarsa assumes we condition on action A. Okay, so we want to find the action value function, and this action value function, it's the estimated return given that you start with the current action A. So because we condition on that action A, we don't assume it was sampled randomly, so we don't have to consider its weight, so probability according to the target policy over probability according to the behavior policy within the importance sampling ratio. Okay, so in a nutshell, it's because in SARSA we condition on AT, so we don't have to determine what's the likelihood of that action. Second, why do we end at time t plus n the importance sampling ratio instead of t plus n minus 1? It's because if we go back here, so in the end step SARSA, the target here involves the action at time t plus n, whereas if we go back to the TD here, let's go back here. Okay, so TD, we said it's the same reward than end step method, TD method, so let's go back many slides. So TD, sorry for that. Okay, so this is the end step TD reward. We see that the action at time t plus n, it's not considered because the bootstrapping term only considers the state at time t plus n and not the action. So because the target does not depend on action at plus n for TD methods, whereas for the sarsa method, sorry, let's go back to where we were. Yeah. So here, because for the n-step sarsa method, there is some AT plus n, then we have to consider the relative weight of its probability under the target or behavior policy. So this is why for n-step sarsa, we do have to include action AT plus n in the importance sampling ratio because this action is part of the target. Whereas for TD, action t plus n was not part of the target. The target considered only actions until t plus n minus 1. Okay, so this explains why the importance sampling ratio is slightly different in the n-step sarsa method than for the n-step TD method. Okay, so again, the n-step sarsa method can be used both in a prediction setting or in a control setting. Okay, so what we've shown earlier, it was the prediction framework where you have a fixed policy and you want to refine its estimate based on an n-step sarsa off policy method. But now that you are able to estimate the value function of a fixed policy pi, then you can do periodically policy improvement steps. So this now becomes a control problem instead of a prediction problem. So based on the estimation procedure for the Q function presented earlier, if you do regularly policy improvement schemes, then this becomes simply the control version of the n-step sarsa algorithm. Okay, so every once in a while, or you can do that every once in a while, but you can do that on every time step. You can do the following. So here, if you do that on every time step, you can do the following. So at time t plus n, because you update the action value function associated with state st, you can do the following. You can check what is the new greedy action for state st at time t plus n, the new greedy action being equal to the action maximizing the q function in state st. And then you can define your new policy. So this is the policy improvement step. Your new policy assigns a probability exactly equal to 1 if action A is the greedy action in state st, or a probability of 0 otherwise. Okay, so basically what you do is you, based on your new estimate of the value function, you build your new policy to make it greedy with respect to your uh, state value function. Okay, and once again, you can do exactly the same thing for expected sarsa instead of sarsa. Okay, so you can have an n-step off policy expected sarsa method, and this both in a prediction or a control setting. Okay, so for the end step off policy expected sarsa, you can define the returns exactly as you did for the on policy end step sarsa. Okay, so the return would be, sorry, not the return, but the target. The target would be the sum of the discounted rewards in the next n steps plus an indicator which is worth 1 only if the episode has not finished at time t plus n, and this now multiplies gamma to the power n times the bootstrapping term, where again the bootstrapping term is meant to reflect the expected rewards starting expected discounted rewards starting at time t plus n. And for the expected sarsa, it's not the q function at the action at plus n itself. It's a weighted average across all possible actions of the various possible actions under the policy pi times qt the times the action value function at state st plus n under the various actions. Okay, so now this weighted average, of course, if you have a greedy target policy, then let's say, so if you work in an off policy setting, you might have a greedy policy, and in that case, this summation would contain a single term, where this probability would be 1 for the greedy action and 0 for all others. So you would only have the q function at state st plus n and the greedy action in that state. Okay, so if you consider a fully greedy policy for the target policy, this would contain a single term here, which would be the action value function for the greedy action at time t plus n. Okay. So I'm just reading the note here. We don't use the behavior policy for estimating the value of the policy. Okay, so here it's because this is the q function which estimates expected rewards under the target policy and not under the behavior policy. Okay, so why this note is here? It's because this pi, you might be thinking, are these the probabilities under the behavior policy or the target policy? But this is really probabilities under the target policy, not the behavior policy. Okay, so it's really a pi, it's not a b here. Okay. And now, so this defines the target. Now, what is the update rule? Well, it's exactly, or I'd say, almost identical than for off policy sarsa. So again here, at time t plus n, you only update your estimate for the state st and action at, and then you use the following rule. So the next estimate is the previous estimate plus, learning rate times importance sampling ratio times the target minus the previous estimate. So it's always the same kind of logic for the update rule. But here, again, what changes every time in the various versions of these algorithms is the importance sampling ratio. So here, uh, it starts at t plus 1. So because when we estimate the Q function or the action value function, we condition on the first action, so we don't have to consider its probability. So excluding action AT makes the importance sampling ratio start at t plus 1. And furthermore, here, why do we end at t plus n minus 1? It's because if we go back here, we see that in the target, the action at time t plus n is not considered. Okay, so this is not a t plus n. This is just a sum of the various actions. So the action t plus n is not taken into account in the target. So we also have to exclude it from the importance sampling ratio too. So this is why this ends at t plus n minus 1. Okay. Okay. So this is great, but we've seen that all the off-policy methods considered use importance sampling. So one could say that this can be, well, it can be fine, but it can also be irritating if the importance sampling ratio is very volatile. So we've seen extreme cases where when you have a greedy policy as the target policy, many chunks of episodes are disregarded or discarded within the learning because the importance sampling ratio becomes 0. Okay, so this can be irritating if you discard many chunks of episodes in learning or if the importance sampling ratio is very volatile. So one might be wondering, is there a possible approach for off-policy learning which does not rely on importance sampling? So in the one-step case, we saw in chapter 6 that this was possible. Okay, so the Q learning, if you go back to your slides from chapter 6, the Q learning algorithm was an off-policy method, but it didn't rely on importance sampling at all because you can see it's a particular case of algorithms within this section, but with the importance sampling ratio containing 0 action, so the importance sampling ratio could be set to 1 all the time. So there was in fact no importance sampling ratio. So the question we might ask ourselves is, would there be a possible n-step algorithm for off-policy learning which does not rely on importance sampling? The answer to this question is yes, and there's one of such algorithms presented in the textbook, which is referred to as the n-step tree backup algorithm. Okay, so I wanted to let you know this exists. Details are in the book, but for the sake of the current course, we'll leave that out of scope. So for interested readers, please have a look there. It's part of section 7.5 of the textbook, but we won't dig into the details during the lectures of the present course. So we stop the chapter here, and we'll start chapter 9 in the next lecture, next video. So have a nice day. Take care.